Hello folks, this is Tom from anti-proton.com, and this is the very first video in my little series on how to program. I wish to teach you to program if I can, because everybody should program. It's lots of fun. And in my video, I am not going to teach you anything silly like how to make the computer say hello world. No, we're going to probably program something that actually is usable, something that's not too difficult, but something you can actually do. Something hopefully with nuclear physics twist to it if we can. But before I start out, first off, just so that you know, this is kind of like a preliminary video. This is not actually the one where I show you how to program. This is the video you should watch before you watch that video. And this is an important video, by the way, too. This is kind of a primer for it. You need to know some of this stuff, so just trust me, you should watch it. Later on in the other videos, I'll refer back to things that you should have picked up in this video. So. Now, before I go any further, let me state that usually I give a disclaimer at about this point when I'm doing my nuclear physics videos. I say, I'm not a nuclear physicist. I'm just a layperson who's interested in it, blah, blah, blah. Well, this time I don't have to do that. I actually am a computer scientist. I have a bachelor's degree in computers. I have, how many years? Let's see, 98 to 2008, 9, 10, 11, 12, 13. I have like 15 years of professional experience. That means paid doing it for a living experience, and I've done all kinds of computers. By God, I've been a network engineer, I've been a programmer, everything you could think of. Most people that do computers do very specific, narrow little fields. I've been a generalist. I've done every conceivable thing you can possibly imagine in computers. I've never been a DBA. I do DBA stuff and know how to I know how to be a DBA, but I've never actually been a DBA. That's about the only database administrator. It's about the only thing I think I haven't done of the major categories, of course. Anyhow, so yay, something I don't have to say I'm a layman on. Yay, something I can actually be somebody knowledgeable about. So anyway, let's get into this. I'm going to go with you know what a computer is. If you don't, then I don't know what to say. So we're going to talk about programming and what programs are. Your computer is controlled by a central processing unit. It's a little thing that sits in the center, like these two guys right here. This is an old AMD like K7 or something processor, and here's a what's upside down? Here's the cliche Intel Pentium chip. Intel Pentium. Intel Pentium. You want to focus on that little thing? Okay, it wants to focus. Good. See? Now these little circuit boards have hundreds of little pins in them sometimes more than hundreds, sometimes less than hundreds. And these little pins are made of gold or other metals, often gold like this guy right here. And do you want to focus? Do you want to focus? Focus. I think it's like supposed to have like up close focusing, and it's like not doing it. But anyway, these little pins here connect to the central chip in the middle. And what the CPU does, and oh, by the way, the CPUs are made by these guys. It's an Intel guy, right? Hello, Intel guy. Hello, Intel guy. Are you there? Hello? Hi. Okay, Intel guy's got something else to do. Okay. Well, CPUs are the central processing component of the computer. And what a CPU does is it has a whole bunch of logical components to it called logic gates, which I'm not going to get into too much here. I might make another video on things like logic gates and getting into actual deep computer science stuff. But suffice it to say right this moment, with the simplicity of this video, the logic gates are little electronic constructs that allow a computer to make decisions based on things. You can tell the computer, for example, if you have a switch that's on and another switch that's on, then send power, but if this switch is off and this one's on, don't switch power, and vice versa. And you can give it little sequences like this. And when you can set up little arrangements like this and you have millions of them together, you can make quite complex logical pathways where you tell the computer, if you see a signal coming in from this device right here, take that signal and put it somewhere else or something to that effect. You can get quite complex. And oh god, I need to do a video where I explain the actual details of that and show you some Boolean algebra and everything else. But forget that. You don't need that for programming. That's just other stuff we'll get into. So basically put, now that you have this circuit here connected to your computer, this whole bunch of millions of little circuits, and you can tell it to do stuff, how do you tell it to do stuff? Okay? Well, we'll get into programming, but before we do that, let's talk about how this thing actually works, because it's sort of important that you understand this. Really it is, believe it or not. I have a little thing here I was going to go through and explain how it works. There are things called operation codes. They're numerical sequences that you can feed to this thing, and you can tell it to do stuff. You can say add, subtract, multiply, divide. There's a whole bunches of them. In fact, there's probably like about 100 for this little guy right here. This is called a CISC processor, complex instruction set computer. It can actually have many, many different ones. You can tell it to left shift numbers and right shift numbers and do all kinds of funny stuff. But basically, take a simple command. Let's take a really simple one like add, okay? You say the operation code add, and that will have a number like, let's say 1, 2, 3, 4, whatever its numeric value is. And then you'll have two operands, the little things that come afterwards. So you'll say add 1 and 4. And the computer will then store the result of 1 and 4 being added, which is 5. You're thinking, wow, that's really simple, right? I mean, that's like one calculator instruction. That's the level that these things do processing. They don't really do very much. They do very simple things. But they can do so many of them per second that you get this grand illusion that all this stuff's happening. But the reality is it's very simple little instructions. It takes about 14 instructions to put a single dot, a single pixel on the screen, about 14 instructions to do it. And if you ever want to know them, I can show them to you for this processor right here. In fact, I remember writing a graphics driver for a processor like this one time. Not for this processor, but for something that used a processor like this. It took about 14 instructions to put a dot on the screen. Anyway, so now that you have these numbers, and just imagine giant sheets of paper that have numbers that tell you that if you input this number, it means add. If you input this number, it means subtract, multiply, divide. The next number that you input is the number that's being worked on, and the next one is another number that's being worked on. And you can give it instructions like store, and a value to store, and a memory location to store that value in. So now that you have these, you could sit down and you could take out punch cards like this. Punch cards, yeah, the real deal. A whole bunch of them. And you could literally feed numbers to the computer, all these little strings of numbers, and the computer would do all kinds of things for you, fetching data, moving stuff around. That's how this stuff was originally coded. People like Bill Gates originally, I mean literally Bill Gates actually did code stuff, believe it or not. I mean he actually did write codes before he became rich. People like him and other programmers from back in the days of yore would sit down and they would actually punch out these little numbers. They would look in books and they would see what they wanted to do, and they would add values and stuff, and it was very complicated. They came up with something a little while later called assembly code. They said, look, we have a number that tells us what to do, and then we have, let's say, two numbers we might operate on. Some systems had different arrangements. If this number, 1, 2, 3, 4, always means add, can't we write a program where I could just write the word add and it would just convert it for us so that we wouldn't have to know the numbers? Basically a program that does the lookup for us. So we can type add, subtract, multiply, jump to another part of the program, return back to the other part of the program, store memory, fetch memory. So we can just type these things in English, and then this little program would run across and just flip everything over to its exact one-to-one numeric operation code. Could we just do that? Wouldn't that be simpler? Hell yeah! So they wrote assembly, and that's what assembly does. It replaced zeros and ones sort of things with words, such as clear a memory location, add to that memory location the number 1, add to that memory location the number 4. Well, 1 and 4 is 5. Print that result out, and it would go along, well, not print it out, but save it somewhere or do something with it. And that's how assembly code was born. That's what assembly code does. Here's my 1994 or whatever it is, 3-4 PC Programmer's Bible, and if you look at it, this is old as hell and it's fair use, so if you look at it, you'll see there's actually codes here telling you, just a little tiny bit, just to give you an idea. There are some codes telling you what to do. See the very top one that says MOV DX, seg, blah blah blah. That's saying move to the location DX, whatever seg. It's been so long I can't remember, but move something to it, move something to do something or other. God, it's been so long. Here we go, like this guy right here, pop DS. That means take from a memory location the value and put it in DS. Push CS takes the memory location from CS and sticks it to a memory location. It's just, actually, those are stack commands. But the point I'm trying to get to is they're still incredibly simple operations. You're not doing anything more than the tiniest operation per line. That was neat. The programmer said, what if I want to do a whole bunch of common everyday things, just stuff that I want to do, like I want to go and grab some memory somewhere. But to do that, I have to make like 10 different instructions. I have to clear a place, I have to set where I want to go look into another location, then I have to tell the system to go look, and then I have to, if I have all these commands in a row, why can't I just say one thing and mean all of that? So it's kind of the next logical extension. This was called macro assembly. We're getting there. Macro assembly said, okay, let's have the assembly like before, but certain functions that are complicated but always the same, we can just write one command and that means all of this. And when you took that that text that you wrote and you fed it through the little macro assembler program, it would expand it out to the full-size program, just kind of making all the commands, kind of putting them all in place where they needed to be. So it was a list of instructions, and some of them were not quite so complex. They were very simple, and like go to the store, and it would say, okay, we'll get in car, drive, find store, go in, come back, and it would just kind of put that there for you. Do you see what I mean? So that's macro assembler. After a while, programmers said, well, that's all neat and everything, but let's make it even better than that. My room's really hot right this moment here. I had to get out of the office and go like in my living room or something where it's cooler. They came up with something called high-level languages. And we're going to now get into high-level languages because that's what we're going to learn to program on. So I just wanted you to understand that that's how these things work. In the low level, the CPU, and I'm talking about the one in your very computer right this moment, simple instructions. Even specialized computers like the one running this Geiger counter right here, specialized processor doesn't do that many things, but has a very specific set of instructions that it can understand, things that it can do. For example, it can handle a tick from the Geiger counter thing here. If radiation hits it, it makes a little tick in its little brain. It stores this little value and increments it and decrements it and stuff like that over time. So that's something kind of that you might need to understand. Let's get into high-level languages. Fast forward a little while into the future. At some point, somebody said, let's come up with a specialized language with special keywords that I can type that are really specialized for certain things. Languages that are specialized for math, languages that are specialized for human language, ones that are specialized for this or that. And I can make special custom commands. For example, the hypotenuse of a triangle. Hopefully you know how to calculate the hypotenuse of a triangle. You have a line here, and you have a line here that's a hypotenuse, and you have a line up and down, right? There's your triangle. You see? Your triangle. And to calculate the hypotenuse, all you have to do is you have to add this part after it's been squared to this part after it's been squared, and then you square root them, and there's your hypotenuse's length, right? Well, in higher level languages, you might create a command, hypotenuse, and you feed it two numbers. You feed it the length of the bottom and the length of the top, and then it just spits back the result. What the compiler would do is a compiler is a specialized program that would take that command and break it down into the 50 or 60 little individual operation codes required to do that. Like one operation code squares the number. It takes the number and then it does the multiply command I talked about earlier, and it spits out the result, and then it saves it somewhere, and then it goes fetches the next number, and so on. It has all those little things to do, but it's one line for you when you type it as in the program. That's very, very important because all of these things are having the same common theme. They're making it easier for human beings to interact with a computer, because a computer is a programmable machine. But the more easily that you can program it into more complicated functions with less actual work, the better for the programmer, the better for everyone, and that's the whole point of computer languages. You ever heard somebody say, well, if there's so many different languages, why don't they just make one language that's the best language? Why have all these different languages? Because each one is specialized for a different function. That's the whole point of computer languages in the first place. We're going to look at Java in the next video when we actually learn to program something. I just kind of want you to get into some of this sort of stuff. So you had compiled languages which take the human code that you write out, ask a person for the name, get the name and store it in this little variable here called name, and then print out the value of name. If name is equal to Tom, then do this. If it's not equal to Tom, do that. And these higher level concepts are broken down into zillions of little instructions, individual ones, dozens and dozens of them. For example, I might say put a red dot on the screen right here. That turns into 14 instructions to put that dot on the screen. That's a higher level language like C, C++, Java, Visual Basic, C#. I don't want to say Objective-C because I really hate Objective-C, but technically, yeah. Now, modern day languages come in two types. There's a third type too. technically speaking. But you have compiled languages and interpreted languages. A purely interpreted language would be like BASIC. What you do in BASIC is you type out the program, and instead of having it converted to this machine code, which is saved somewhere that can be executed without anything further done to it, what the interpreted language does is it has a program that sees each line and decodes it and turns it into what it's supposed to be, and then sees the next line and decodes it and turns it into what it's supposed to be. So you have to run an interpreted language inside of an interpreter. BASIC is a good example of that. Without the BASIC program, you can't run a BASIC program. So I could write a program that does something, but by itself it cannot just run. It has to be fed through the interpreter, which then communicates with the CPU and makes it do stuff. BASIC was a good example of that. Certain implementations of older Visual Basic sort of are like that too. You have a lot of scripting languages fall under that category, like JavaScript, for example. JavaScript itself, you can't just make, well, there's sort of a way, but typically speaking, you can't make Java just sit there by itself and just run. It's got to be run by something. Your web browser runs it, for example, using a Java script engine. Then on the other side of the field, you have compiled languages. What happens in the compiled language is all that code that you write out gets compiled into a huge amount of machine codes, these little operation codes I told you about, and they get stuck into something like an executable, like remember a .exe program or a .com program. And these exe programs can stand alone because they're now nothing but machine language that the computer can start just kind of doing, feeding straight to the processor without needing anything else. But you have to have that compiler at that initial time, or else you won't be able to turn it in there. The only way to get past these two and not involve them is to write pure machine code yourself. I've done that. It's really hard, but I did it. It's really hard. Even when you're using assembly, you still have an assembler, which is kind of like a compiler, except it doesn't really break it into anything. It just kind of swaps human word for operation code. Okay? The hybrid in between these two are what's called compiled interpreted languages. Java is actually a good example of that. Most .NET applications work the same way too, like C# and everything. What they do is they compile, but they do not compile for a specific processor, because remember, this processor has operation codes it understands, like how to add and subtract, but a different processor, well, these two have the same codes, but technically speaking, a different processor could have a completely different set of operation codes. They do the same things, but they may be arranged differently, kind of just like a different language. And so if you compile for this, and it takes the code that you've written and converts it into the little operation codes, they work on this, but they won't work on this because it understands a completely different set. Now, you can take that code that you wrote, and if you have a compiler for this processor, you compile it for this processor. So as long as you have a compiler written for the processor, then you can take the same code and compile it for either one of them. But sometimes you have to make minor changes. With something like Java, what you're doing is the computer makes a compiler that compiles for a virtual processor, a processor that doesn't really exist in the real world. It's kind of like a pretend one. And what happens is when you write something in Java and it's compiled for Java, it's now compiled for this virtual processor. Then what they do is the people who write Java go out and they make a Java runtime, if you like the interpreter part, for every type of processor that there is out there. So instead of you writing code and compiling it for each type of processor and distributing it for each one, if you're running Windows on a PC, if you're running Macintosh, if you're running Linux, instead of doing that with Java, you just write your program. And and Linux, Mac, and Windows, and all of them have their own Java runtimes. So it kind of takes the onus off the programmer. That's the whole point behind an interpreted language like Java. And C# and stuff can do that too. In fact, even old Visual Basic 6 could sort of do that. Something called P code is what it was called. That could do something to that effect. So hopefully that clears up a little bit more of how that works. We're going to learn Java, and we're going to learn how to make a simple program with it. Now, I wanted you to understand the way that some of this stuff works, because when you're optimizing your program and understanding the way things work, it's neat to know how the computer works. So consider this like a little bit of an impromptu lecture. I will be doing two types of things. I will be teaching you to program, and I'm also going to be releasing a couple more videos that are about specific things in very great detail, like operation codes, for example, assembly, how that works, the nature of memory and CPU, some things like that. So we'll get into that. So hopefully this hasn't been too completely off the wall for you. It's been kind of impromptu ad-lib for me. I mean, I actually did have a little sheet I was going to go down right here, but I didn't exactly stick to it, so anyhow. But this has been Tom from anti-proton.com, and did I gab too much? Tell me what you think.